One more. Hello, everyone. My name is Benjamin Mungi, and I'm going to discuss the fundamentals of artificial intelligence. And without further ado, let's dive right in. We're going to start with Module 1, which is the history, the trends, and the future of artificial intelligence. The AI era began in the 20th century with Da Vinci's Mechanical Knight designs to Turing's theoretical machines, focused on symbol manipulation and formal logic. Over decades, the field pivoted from pure symbolic AI through statistical approaches in the 1990s to today's deep learning breakthroughs. These shifts mirrored data mining's journey from handcrafted association rules to predictive neural models. Philosophical debates around weak versus strong AI continue to shape research agendas, raising questions about whether future systems might ever attain true consciousness. And here I would like to talk about my AI agent, Sephora, which is basically a pharmacist assistant, like I said in the previous video, and supposed to predict drugs based on the reported signs and symptoms. So Sephora, a pharmacist assistant, embodies these historical and philosophical currents. Instead of static rule tables, she harnesses machine learning models trained on local Ugandan prescription and outcome data, reflecting the move from expert systems to adaptive, data-driven tools. Her design balances explainability with statistical nuance, situating her as the cutting edge of current AI trends. Looking ahead, Sephora's roadmap anticipates integrating real-time genomics and natural language dialogue, forecasting a future where AI assistants evolve into healthcare partners. And that is more. Let us move to Module 2, Introduction to Problem Solving in Artificial Intelligence. In pharmacy, in a pharmacy context, the initial state captures a patient's symptoms, allergies, and medical history. Operators include diagnostic tests, dosage calculations, and allergy checks. The goal state is safe, personalized prescription. This formalization par parallels classification in data mining, where each patient record becomes a state to be categorized. The frame problem, choosing which patient attributes matter, underscores the challenge of focusing on only relevant data when formulating operators and goals. In application to pharmacy, for Sephora, defining her problem space makes her reasoning transparent and consistent. When a new patient record when a new patient record arrives, she maps symptoms to formal states and applies a hierarchy of operators, first screening for life-threatening contraindications, then running dosage heuristics. By articulating initial state is equal to patient profile and goal state is equal to recommended regimen, Sephora's logical Sephora's logic becomes auditable by pharmacists and regulators. This structure not only clarifies her decision process, but also supports future extensions such as integrating new diagnostic operators or emerging treatment protocols. Module 3, which is problem solving by search. AI search methods range from blind strategies like depth first, breadth first, to informed approaches like ESTA that leverage heuristics. Heuristics estimate distance to a goal, guiding such away from unlikely paths and toward promising solutions. In healthcare, the state space might represent possible diagnosis, and operators transition between symptom sets as tests confirm or rule out conditions. Composite heuristics combining symptom severity, patient age, and comorbidity scores balance speed against comorbidity scores, balance speed against accuracy. Philosophically, each such tree becomes a simulation of clinical possibilities, raising questions about whether an AI truly understands the disease process or explores a decision graph. So far as such method, so far as diagnostic engine uses best first search guided by a custom heuristic that prioritizes treatments, minimizing ad- adverse effects. Under the hood, she clusters similar patient histories to prune the search tree. Much like data mining reduces complexity via grouping, when a patient prevents overlapping symptoms, Sephora navigates through potential diagnoses in milliseconds, returning the top candidates with confidence scores. This information search ensures that high-risk treatments are only recommended when options are exhausted, optimizing both patient and rescue resource utilization. Module 4, Knowledge Representation and Reasoning. Symbolic knowledge representation uses logic and structured schemas to encode domain facts explicitly. Data transforms into information when contextualized, e.g., blood pressure is equal to 140/90, becomes hypertensive. It's trying to say that when a patient's first order logic adds relational expressiveness. Variables, quantifiers, and predicates capture complex drug-patient interactions. The physical symbol system hypothesis asserts that manipulating such symbols can produce intelligent behavior. Debates persist over whether all pharmaceutical knowledge can be formalized or if certain tacit clinical insights elude symbolic capture. Hybrid architecture of Sephora. Sephora's hybrid architecture illustrates these concepts in practice. She stores core values in a symbolic engine. Sorry, I'm not yet done with Sephora. While feeding real prescription data through neural networks to detect emerging side effect patterns. This dual approach ensures that her recommendations remain transparent and adaptable. By encoding both fixed medical guidelines and statistical associations, Sephora demonstrates how knowledge representation and reasoning underpin reliable, scalable AI in pharmacy. And module 5, inference in first order logic. Inference in first order logic relies on system rule application, resolution, unification, and theorem proving to derive new truths from known axioms. Soundness guarantees that no false prescriptions slip through. Completeness ensures that all medically valid conclusions can be reached. Given sufficient rules, automated theorem proving can trace how a particular dosage recommendation follows from general treatment axioms. Yet, philosophical critics like the Chinese room argument question whether symbol manipulation equates to genuine medical understanding. Sephora's inference engine applies these principles to decision support. When confronted with a patient's lab results, she unifies specific data with general rules, deriving tailored dosage adjustments only when every precondition is met. Resolution traces document each inference step, allowing pharmacists to review how a recommendation was reached. Through this rigorous foundation not only bolsters trust in Sephora's advice, but also provides a framework for auditing and certifying AI-driven healthcare systems. Module 6, Reasoning Under Uncertainty. Real-world medical data is noisy and incomplete. Probability theorem and Bayesian networks offer formal mechanisms to quantify and update uncertainty. Conditional independence assumptions enable efficient inference, while utilities weigh treatment benefits against risks. Unlike classic logic, probability handles degrees of belief, critical when symptoms partially overlap across diseases. Philosophical debates interrogate whether all uncertainty can be captured numerically or if some aspects of medical judgment resist quantification. Sephora integrates Bayesian reasoning in Sephora. Sephora integrates Bayesian reasoning to manage diagnostic ambiguity. She constructs networks where nodes represent symptoms, tests, and conditions. Edges encode conditional probabilities derived from clinical studies. Upon receiving patient data, she performs Bayesian updates to compute posterior disease probabilities, then recommends further tests if confidence thresholds are met. This probabilistic framework ensures her suggestions adapt to varying data quality, providing confidence score diagnostics that support informed decision-making. Module 7, Planning. Planning in artificial intelligence sequences actions to achieve defined goals. Strips operators specify preconditions and effects, enabling an agent to compose multi-step plans. Unlike single-step problem-solving, planning handles partial ordering and dynamic environments. A firm problem reemerges, choosing which state variables to monitor when predicting action outcomes. Hierarchical task network, HTN, planners mitigate complexity by decomposing tasks into subplans, reflecting how clinicians break down treatment protocols. Sephora's care plan module. Sephora's care plan module exemplifies these planning concepts. Given a prescription goal, she defines actions like administer dose, schedule lab tests, and send refill reminder, each with preconditions and effects on patient state. When a patient misses a dose, Sephora replans, adapting follow-up actions to maintain therapeutical levels. By structuring care as a dynamic plan, she ensures treatment adherence and continuity, transforming static prescriptions into responsive, patient-centered action sequences. Module 8, Planning and Decision Making. Linking planning with utility theory yields decision frameworks that optimize outcomes under constraints. Markov decision processes model sequential choices in stochastic environments, satisfying the Markov property. Policies map states to actions, while value functions quantify long-term rewards. Real-world planning must also consider resource limits, multiple stakeholders, and ethical trade-offs, inviting interdisciplinary reasoning that spans interpersonal and intrapersonal intelligences. Sephora uses a model called Markov decision process to guide treatment decisions. Each situation or state includes things like how well the patient is following treatment, any side effects, and their financial limits. Her possible actions include changing medications or referring the patient to another specialist. She runs a method called value iteration to find the best strategy, one that balances medical effectiveness, side effects, risks, and cost. This way, her recommendations aren't just medically sound, they also respect the patient's overall needs and preferences. Module 9, Machine Learning, which is our last module. Machine learning builds models automatically from data. Supervised learning handles tasks like predicting drug effectiveness based on patient traits, e.g., classification, regression. Unsupervised learning finds hidden patterns such as new groups of side effects, e.g., clustering, association. Reinforcement learning would help design smart adaptive dosing plans that adjust over time. Philosophers and scientists still debate whether machines can truly outperform human experts in spotting patterns and making clinical decisions. And this Sephora's predictive core. Sephora's predictive core uses supervised models to forecast the best medication for new patients. Training on labeled pharmacy records, regression submodels estimate individual dosage curves over time, while clustering module flag unusual reaction patterns for pharmacist review. Continuous retraining on fresh data ensures her performance and patient safety improves with each interaction. In this way, Sephora transforms raw healthcare data into actionable insights, embodying the full spectrum of modern machine learning. Thank you so much, and don't forget to like and subscribe.